The purpose of today's video is to teach you about ICE tables, an organizational tool for solving equilibrium problems. In this video, I'll specifically focus on using ICE tables with KSP problems, or solubility product constant problems. I'm going to make up a fake reaction here, 2A plus B in equilibrium with C, and let me quickly just state, sometimes you'll see ICE tables called Rice tables. The R in Rice tables stands for reaction. The other rows, as you might have guessed, spell out ICE, and they stand for initial concentrations, change to concentrations, equilibrium concentrations. And I'm going to start out with a reaction mixture that is 1 mole per liter of A, 1 mole per liter of B, and just for simplicity's sake, I'll start out with 0 moles per liter of C. Now, for reasons that will become clear in the future, I like to separate my reactants from my products. This reaction is clearly not at equilibrium. How do I know it's not at equilibrium? Well, the reverse reaction is impossible. I will not have C becoming A and B because I don't have any C to begin with. So what's going to happen to the amount of C as this reaction works towards equilibrium? It will increase. In fact, it will increase by X. If C is increasing by X, B will decrease by X. And if we look at the mole ratios here, for every B that I use, I'll use up 2 A's. So A will decrease by 2X. And I'm fond of saying that the E row is actually the easiest row because it's simply 1 minus 2X for my concentration of A, 1 minus X for my concentration of B, and 0 plus X for my concentration of C. So we can use this tool to organize our thoughts around equilibrium problems, and you can see that it's simply combining stoichiometry and the concept of equilibrium. As we go to do some more work with this, I would like to focus specifically on lead-2 fluoride KSP problems. So lead-2 fluoride has a solubility product constant of 3.6 times 10 to the negative 8, and I want to answer 2 questions. First, I want to answer what mass of lead-2 fluoride will dissolve in 750 milliliters of pure water, and then I want to ask the question and answer what mass of lead-2 fluoride will dissolve in 750 milliliters of 0.95 molar sodium fluoride. This is going to illustrate something called the common ion effect. Alright, so on to the application of this with KSP problems. What mass of lead-2 fluoride will dissolve in 750 milliliters of pure water? Quick reminder, the KSP for this is 3.6 times 10 to the negative 8th. Just a quick reminder from class, this reaction is lead-2 fluoride solid dissolving in water to form the lead-2 ion plus 2 fluoride ions. And both of those are aqueous. I'm just not writing them. I wrote solid because I remember that the solid doesn't factor into equilibrium. I'm going to divide my reactants and products, and I'm going to label my rows, and I'm going to label them under the lead-2 fluoride because, again, the concentration of lead-2 fluoride doesn't factor in, it's a solid. Now, to start out, in pure water, what is the concentration of lead in pure water? You and I better hope that it's 0. There is fluoride in our water, but in pure water there is not. So is this reaction at equilibrium? Well, no. 0 times 0 does not equal, 0 times 0 squared does not equal 3.6 times 10 to the negative 8th. Let's see what's going to happen. Well, to get to equilibrium, I'm going to need to form some lead-2 ions, and for every lead-2 ion, I will also form 2 fluoride ions. That means that my concentration of lead-2 at equilibrium is going to be 0 plus X, and my concentration of the fluoride ion at equilibrium will be 0 plus 2X. Well, let's take a look at this equilibrium expression. We know that the equilibrium expression is going to be the concentration of the products at equilibrium over reactants. That's over 1 here because the reactant is a solid. And we know that's equal to the value of K, which in this case is 3.6 times 10 to the negative 8th. But I also know values for the concentration of lead-2 and the concentration of fluoride. The concentration of lead-2 at equilibrium is X, and the concentration of fluoride is 2X. And so that's going to be 2X squared. Remember, the concentration of lead times the concentration of fluoride squared. And when I solve this for my concentration, when I solve this for X, X is going to be 0.00208. And the nice thing is this is moles per liter. And this represents my concentration of lead-2 at equilibrium. Going back up to the original problem, what mass of lead-2 fluoride will dissolve in 750 milliliters of pure water? Well, how will I know how much lead dissolves? Well, if I am going to make 0.00208 moles per liter of lead-2, that must mean that 0.00208 moles per liter of lead-2 fluoride dissolved. So I'm just going to do some quick dimensional analysis. 750 milliliters times. In order to get a concentration of 0.0208 moles per liter of lead-2, I must have dissolved 0.00208 moles of lead-2 fluoride in every 1,000 milliliters of water. And the molar mass of lead-2 fluoride is 245 grams for every 1 mole. So that means in 750 milliliters of water, 0.3822 grams of lead-2 fluoride will dissolve. Keep that answer in mind as we look at our next problem. Okay, for me things get interesting with this problem. It's the same reaction. We're still going to be dissolving lead-2 fluoride, and I'm going to remind myself that this is a solid and it's going to be in equilibrium with the aqueous ions of lead-2 and fluoride. And again, K for this reaction is still 3.6 times 10 to the negative 8th. That's my KSP. Let's separate products and reactants. And again, I'm going to label my columns here because the solid doesn't matter. This question differs a little. It says, what mass of lead-2 fluoride will dissolve in 750 milliliters of 0.95 molar sodium fluoride? I'm going to start by asking myself the same question. What is the concentration of lead-2 in sodium fluoride? Well, there is no lead-2 in sodium fluoride, so that's 0. And now, what is the concentration of fluoride in 0.95 molar sodium fluoride? Well, that's actually 0.95 molar, because for every mole of sodium fluoride that's dissolved, we'll get a mole of fluoride ions. Is this reaction at equilibrium? Well, no, because since there's no lead, the reverse reaction still can't be happening. So I'm going to be increasing, as I go to equilibrium, some of this lead-2 fluoride will dissolve. I'm going to increase this by X, I'll increase this by 2X, and so at equilibrium the concentration of lead is lead-2, and the concentration of my fluoride ion is going to be 0.95 molar plus 2X. Let's see how this is going to work out. I'm again going to plug this into my equilibrium expression. We'll get 3.6 times 10 to the negative 8th is equal to my concentration of lead times my concentration of the fluoride ion squared. Now here's where I need to do a little bit of thinking. This tiny value for K means that at equilibrium I'm not going to have many products. And so 0.95 plus 2x, well 2x is really small. In fact, let me write this again. I'm going to get 0 plus x times 0.95 plus 2x squared. Well, 0.95 plus a really small 2x, that's really like saying 0.95 plus a negligible number. A lot of times students have questions, why isn't x negligible here? Well, you have to remember x here is 0 plus x, and something can't be negligible with respect to 0. We'll check at the end to see if my assumption made sense. So now we have 3.6 times 10 to the negative 8th is equal to x times 0.95 squared. When I solve for x, I'll get that x is 4.0-ish times 10 to the negative 8th moles per liter. And as I use that value to find out what mass of lead 2 fluoride will dissolve, 750 milliliters times 4.0 times 10 to the negative 8 moles of lead 2 fluoride per liter. Oh, sorry, I shouldn't say per liter. Divided by 1,000 milliliters, so that's per every 1,000 milliliters, times 245 grams per mole. And I will have how much lead 2 fluoride will dissolve in 750 milliliters of 0.95 molar sodium fluoride. That's going to be 7.3 times 10 to the negative 6th grams of lead 2 fluoride. And you'll notice I asked you to keep the other number in mind. This is a substantially smaller amount of lead 2 fluoride that will dissolve. And let's go back up to the top and think about this from a conceptual standpoint. I have quite a lot of fluoride particles. In fact, I have 0.95 moles per liter. And so the probability that some fluoride will bump into some lead 2 and react is quite high. I don't need much lead 2 at all to reach equilibrium. This is something called the common ion effect. Lead 2 fluoride and sodium fluoride share the common ion fluoride. And because there is fluoride present, that will impact the equilibrium reached between the lead 2 fluoride and its ions as it dissociates. Really, you might come across the name common ion effect. You might come across that as a multiple choice question, but really you're most likely to see that in something like Scholastic Bowl. Quick recap of this method. I was able to say that 0.95 plus 2x is essentially equal to 0.95 because the value of k is so small that I know my products being formed are going to be very, very small as I go towards equilibrium. And also, when I found x, I was able to say, well, the moles of lead 2 that are generated, that had to come from lead 2 fluoride dissolving. And so that's how I was able to say the x moles per liter here was equivalent to x moles of lead 2 fluoride per liter dissolving. Hope you found this helpful.